All right, hey class. Today I'm going to be doing a quick video on NAND gates. A couple things before we start. One, if you're watching this video, I recommend putting it in like 1.25x speed or even 1.5 times speed if you feel like you're able to process information quicker. I know the video sometimes can be a little slow, so by speeding it up, as long as you're able to follow and pay attention, it'll just make it a little quicker for you guys. Secondly, please check your grades. I'm pretty sure everything for the third marking period is already in. So unless you see an error there, that's going to be your grade for the third marking period. Awesome job. You guys did great. Really proud of you. This was kind of my first experience with you guys. So as far as I'm concerned, I thought everything went really well, especially in light of this remote learning situation we're in. So keep up the good work. And I'll end up giving you guys I'll make another video just to directly talk about all the feedback you guys gave me, which I really appreciate. The people that made the videos, they were awesome. It's exactly what I was looking for. Just very informal. Hey, this is how it's going, because I don't really get a chance to talk to you guys now. So I appreciate that. But as far as today, we're going to get into NAND-only gates. The idea is that we're going to take what we learned about AOI logic. And remember, AOI stands for AND or inverter, as far as circuits that are built with AND gates, OR gates, or inverter gates, which is basically what we've learned up to this point. If you remember the Monday before we left our last class, basically while we were in class, I did a very brief introduction to NAND gates, and I also did NOR gates. I kind of rushed through it, so maybe this will jog your memory a little bit, but essentially an AND gate looks like an AND gate. Just a big D with a little dot at the end. And we have, A, B, and essentially it's the same as a AND gate with an inverter at the end. So if this was A, B, if this was A and B, this would be not A and B, and we know that that's the same now as if we De Morgan's it, not A or not B. And our truth table would look something like this. 0, 0, 0, 1, 1 would be 1, 1, 1, 0. Basically the opposite of an AND gate. Remember, an AND gate would have been 0, 0, 0, 1. It's only a 1 when they're both 1. Well, now it's the opposite because it's not A and B. So it's a 0 when they're both 1, and it's a 1 for everything else. It's a NAND gate. And you guys, I had you guys write this down. So hopefully check your engineering notebooks, and you're going to want to use these when you're doing the activity. But you want to set up your equivalents. So we have our inverter gate, A, this is Z, right? The equivalent is going to be A goes into a NAND gate, output Z, and that's all it is. Essentially, we know that this would be A, this would be Z, 0, 1 are only options. We know this is just the opposite, 1, 0. Well, for this, right, there's two inputs to a NAND gate. A, B, this is Z. We would have 0, 0, 0, 1, 1, 0, 1, 1. And if you remember the output, I said it's 1, 1, 1, 0. Well, A and B have to be the same, so this doesn't matter, and this doesn't matter. So if we look at A, when A is a 0, Z is a 1, and when A is a 1, Z is a 0. Just like this, A is a 0, Z is a 1, so they're identical. So this is really all you want to have written on your chart. This is the equivalent of that. Next one we have is an AND gate. AND gates, we know, two inputs, A, B. And what this looks like would be just two NAND gates. And again, we have A and B coming in. And we know that this output, right, would be A, B. Well, here we're taking the opposite, right? Not AB. Oh, I didn't finish that. And then we're inverting this, right? Remember, this is the same as an inverter. So we're getting not AB. And this just simplifies to AB, because we can get rid of the two nots, right? Part of our Boolean theorems. So you don't need to have this in there, but this is your equivalent of an AND gate. And it takes two NAND gates. And then the last one, obviously, is our OR gate. Here's our output. Again, A, B would be our inputs. And what this looks like is three AND gates. This is A, this is B. And again, we're getting, we want an OR, right? So let's prove this. This becomes, again, this is an inverter, so this becomes not A. And this becomes not B. And this is a NAND gate, right? So this becomes not A and not B. So we know we can De Morgan's them. Break the line, change the sign, right? So this becomes not A or not B. Which again, a not just becomes A, or a not just becomes B. And that would be our answer, right? So OR gate, we know, we can see, converts to an OR gate here. And that's essentially just proving these out. And if you guys didn't totally follow that, that's okay. Just want to show you guys where that comes from, but this is essentially what you want to have. Use this whenever you're doing, you guys already drew this, use this whenever you're doing the problems. These are all the equivalents, right? This is our AOI logic, and this is our NAND equivalent logic, right? This goes to that, this goes to that, this goes to that. And I just kind of proved you guys why they're the same. So now what I want to do is just go through a quick example. Let's do, the process is going to be basically starting from a logic expression. We want to implement AOI logic first. And then once we're in AOI logic, we want to replace all the, each individual inverter, each individual AND, each individual OR with the equivalents that I just had here that you guys have the cheat sheet for. And then redraw the circuit with all those equivalents. And then once we do that, I'll go over how we can start eliminating some of these back-to-back inverters. And that's kind of a shortcut. And that's where we get some of these savings. So I'm going to start with the equation Z equals B, not C, or AC. So again, we know we have three inputs. So I'm going to do A, B, C. Just draw my lines down. And I see I have B, not C. It's an AND gate. And it's B, not C. So that's our inverter. And we also have AC. So grab here, A, C. The last thing I want to put is an OR, right? And that would be our Z. And this is our AOI logic. And what I'm going to do is essentially going to redraw this using our NAND-only implementation. So use your cheat sheet if you're not familiar, but the first thing I want to do is I'm going to do this inverter. I'm going to redraw that using my equivalent, which becomes this guy. And this is essentially the same as that. And I have this going into an AND gate. So now I need to draw my AND gate. If I remember what an AND gate is, it's this. This goes back to B. So this is my equivalent of this. And I say I have another one down here, so I'm going to draw another one. I forgot to do this here. You guys got to call me out on this if you see it. Joking, obviously. And then here, right, the two inputs to this equivalent is A and C. So I'm going to pull A and C. And now, again, this is the equivalent of this. The last thing we need to do is we need to draw our OR equivalent. So I'll draw this out here. Remember, ORs have 3 NAND gates. And this will go to Z, just like this does. And something like this. And these 3 are equivalent to this one. So now we have our equivalent circuits. Same output, but this one's using NAND only. Now, if we look up here at this first one, I see that I have 1 OR gate, 2 AND gates, or I'm sorry, 1 inverter gate, 2 AND gates, and 1 OR gate. So essentially 4 gates, but I would still need 3 chips, right? 1 inverter chip, 1 AND chip, and 1 OR chip. And this has 1 gate, 2 gates, 1 gate. Down here, I have 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 gates, and there's 4 gates per chip, so I would need 2 NAND chips. So already, this was 3 total chips. This has 8 gates. This was only 2. So this one right away is already a cheaper circuit because I only need 2 NAND chips, integrated circuit chips. They have 4 gates on each. But I can simplify this even further. Keep in mind that an inverter is the same, right? It's a NOT. So anytime we have back-to-back inverters, it's the same thing as saying, right? This is A. This becomes not A. This becomes not A, which is the same thing as A. We don't ever need 2 inverters, right? Because this is the same as that. We can just eliminate them. And that's what happens when we want to simplify these. We're looking for now, instead of inverters, we're looking for inverter equivalents, which is anytime we see these 2 next to each other, inverter, inverter, whatever this is, right? Call it X, this becomes not X, this becomes not X, and we can eliminate those, right? It's the same, so there's no need to really have it. And that's what we're gonna look for here. Anytime we have back-to-back inverters. So I say I have an inverter here, nothing on that side, nothing, that's not an inverter, that's just a NAND gate. So we're fine there. Again, this is just a NAND gate. This one here is an inverter, so I look back, not an inverter, because it has 2 different inputs. If I move forward, oh, another inverter, right? Because they're tied together and tied together. You can eliminate this. I don't need them because it's going from not A, not C, not, and then not. you don't need them. So I can get rid of those two. They cancel each other. And I'll start down here. I see this is just a NAND gate, 2 separate inputs. This one's 1 input, right? Same input, so that's an inverter. Keep going forward. Oop, this is an inverter here, right? Same input, same input. So I can cancel those. And this one here, again, it's not an inverter. So I'm gonna redraw this up here and get rid of the AOI logic circuit. And what I have is, I have this guy, this guy, right? That's that guy, that's that guy. This gets canceled out, this gets canceled out. This one's still here. It's these two coming in, right? And then canceled, canceled. This goes to Z. And now what we have is 1, 2, 3, 4 NAND gates, which is just one NAND chip, IC chip. And essentially, we went from 3 integrated circuit chips with AOI logic down to just one NAND IC chip. So it's a third of the volume and a third of the cost to build this circuit, Z equals B not C, or AC with NAND-only logic. And that's essentially the idea behind NAND-only. Go ahead and take a run at trying to do a couple problems. Really, you're only doing problems 1 and 2. And we can't do the multi-sim, we can't do the breadboarding, unfortunately. And then answer the conclusion questions. This is going to be due Friday for you guys. I'm going to post solutions, so if you're struggling with it, solutions will be posted. Verify your K-mapping. Make sure you're doing that correctly. That's going to save you a lot of time, so you're not doing the Boolean simplification. But that is essentially NAND-only logic. Use your cheat sheet that you created. Good luck, and let me know if you have any problems. And please email me if you think there's an error with your grade. Thanks, guys.